Salam sejahtera, everyone. So today we are going to learn what is geochemistry. So this is course SIG 2002, and you are going to learn what is geochemistry, right? I will start talk about some introduction on the geochemistry, and then I'll talk about a little bit on the some aqueous geochemistry, what is pH, and also the alkalinity, and then the redox potential, and then I'll go to some thermodynamics, right? So I'll mostly focus on the low temperature geochemistry. So geochemistry, right, is the studies of the origin, evolution, and distribution of chemical elements on Earth, which are contained in the rock-forming minerals and the products derived from it, as well as in living beings, water, and atmosphere. So geochemistry is a very wide subject, right? It may include anything, right? And it involves rocks, right, and minerals, and then also the chemistry of it, right, and includes the solid phase and also liquid phase and even gaseous phase substances, right? And all these are subfields of geochemistry, right? So this is we have aqueous geochemistry, and then we have biogeochemistry, which you have biological component in it, right? And aqueous geochemistry, it's as its name, right? It's more on rival substance in the aqueous phase, right? And then we talk about these cations, anions in its dissolved form, right? And or its dissolved phase, and everything about the liquid, right? And then there is a cosmochemistry, right? Cosmochemistry deals with stuff about the material, right, from outer space, like including meteorite, and the studies of these other material that derive from the outer space. And for example, the moon, right? You have a moon the samples, then and also a lot more, Mars. And then we have isotope geochemistry, and isotope geochemistry talk about the isotopes, right? And I think we are going to learn what is isotope geochemistry in the later, right, in the course, and it is a very useful tool, right, to study the processes, right, the chemistry and whatnot involves in the sample, right? Like how and why and what's the chemical processes that happens when the forming of these minerals, for example, or the rocks, right? So it is pretty useful. It's not just for rocks. I mean, even living things, we can look into the isotopes, geochems of living things, right? And we can know the diets, right? And then also there's a lot more, right? And mostly we are going to also it is useful for geologists to know isotope geochemistry, because most of the samples that geologists look into is those fossils, right? And fossils and rocks, and all these fossils, when if we look into these fossils and understand its isotopes, right, and then we could interpret and understand what are the major processes, right, happens and during the its formations, right? So it may gives us a hint or indications about the paleo environment when these fossils was being deposited or being formed. Okay, and then also we have organic geochemistry, and organic geochemistry is also pretty broad, right? We can look into whatever organic substances, like for example oil and gas, and then studies of oil and gas, and also some biological samples as well, right? As long as it involves organics, and then also less photogeochem, right? Photogeochemistry, it's less how to say studies in this course, and then also there is a regional geochem. So basically, as I mentioned just now, geochemistry is broadly divided into high temperature and low temperature geochemistry. High temperature geochemistry, we deal with samples with high temperature, right? And those samples that forms in high temperature environment, for example, the upper mantle, right, and also below the crust, wherever below the crust, and then also the lava, right, on this magma, and those environment, right, these samples are high temperature, whereas most of the surface samples are low temperature environment, right? So it is much more common if we studies the samples that form and or preserve, right, in this earth surface. So all these involve or can be included into the low temperature geochemistry component. Okay, so what do geochemists do? Right, geochemists study the composition, structure, processes, and other physical aspects of the earth. So they examine the distribution of chemical elements, right? So these is the fundamental thing, right? Geochemistry looks into the chemical elements, right, and in the rocks and minerals, as well as the movement of these elements into soil and water system. So most of the geochemists, when we study samples, right, often geochemistry will measure the chemical elements in these rocks, right? Mostly may involve the dissolve or the dissolution of these rocks, right, using acids or bases, right? And then when it is dissolved and the sample is being analyzed by some instruments, right? For example, ICP-OES or the atomic absorption spectrometer, right? To study or understand the concentrations of these chemical elements in the rocks. And we have more samples, right? Say samples collected from location A, right? And then also we collect samples from different locations like location B and C. Then if we have all these concentration different locations, right? Then we may know the distribution of these elements, right, in those in all this the samples, right? And then we need to interpret the results or the data to know, right, to scrutinize or analyze what's going on, right? So it may help us to solve a lot of problem, right? We may know the question, we may answer the questions of how or why and these elements form in that way, and under which under what circumstances, right? What condition and what processes. So understanding the chemical composition of rocks, right, tells oil companies where to drill for oil, right? And it enables scientists to put together broad-based theories about the way the earth is changing, right? Or it helps environmental management companies decide how to dispose of toxic or hazardous substance. And still mining companies towards use of natural resources with a minimum environmental impact. Okay, so let's look what is molarity and normality, right? Concentrations. Okay, when we look, we study samples of these rocks, right? In water samples, we deal with concentrations. We look in when we want to know how much the substance, right, is in a sample, right? And then how do we know, right, how much, right? So we have to analyze it, right? And then compare it to standards, right, to know exactly what concentration is the elements of interest in the sample. So molarity, right, is defined as the number of moles of solute per liter of solution. So this is per liter, and then whereas molality, right, with a small m, is defined as the number of moles of solute per kilogram of solvent. So this is we for this we look into the weight, right, rather than the volume. For molarity, right, we look at the volume we measure the volume of the sample is based on the volume, so 1 liter of solutions, whereas a molarity, if we measure the concentrations per the weight, right, of solvent. This is also useful, right, molarity, because some samples, for example, say water, right? So pure water, 1 liter equals 1 kilogram of these solutions, right? And then if we are looking into measuring the concentration of these solute, right, in seawater, which has a greater density, right, and therefore we might need to consider to use the weight, right, so that it is more appropriate, right, to measure seawater, which has a different density. So seawater density is definitely slightly, right, higher than 1 what do you call a kilogram, right, so, in a liter. So we have to be careful when we are dealing with solution with different densities, right, than water. So there is another term, normality, right? So normality is defined as the number of mole, right, equivalents per liter of solutions. So this is the number of mole equivalents, right? And these will take into account the how much exactly the charge, right, of the ions or the solutes of interest, right? So like molarity relates the amount of solutes to the total volume of solutions. However, normality is specifically used for acid and bases. So for an acid solution, N, right, is the number of H, right? N is the number of Hi plus ions provided by a formula unit of acid, right? For example, a 3 mole of H2SO4 solution is the same as 6 normality H2SO4. If you still remember these, and I guess all these it's been taught during your secondary school, I think, mostly in physical chemistry, right, about normality, molarity, right, and so you can if you can recall, so here's the difference between the M, what is molarity, and the normality, N, right? So M and N, what's the difference? The difference is normality considers the number of hydrogen, right, these H plus ions in the solutions. Okay, so when you have a H2SO4, right, 3 mole of H2SO4, right, and then it is actually the same, right, to report the concentration of H2SO4 as 6 normality, because you have a 2 hydrogen here, right? So we take into account the number of hydrogens hydrogen ion, right, in the acid. Okay, if it is let's say if this is not H2SO4, it's not sulfuric acid, but it's a HCl, right? The solution is HCl, hydrochloric acid, and the molarity and the normality of these acids is actually the same, right? Because in HCl there is only one H, right? Only one hydrogen in the hydrochloric acid. So say if you have a 2 mole of HCl, then if we'll report it as also 2 normality of HCl, right? So the number of hydrogen it's the same in this case, right? Same as others. You have hydrofluoric acid. What else? Nitric acids, right? For the difference only matters when we are considering acids or bases with different hydrogen, right? Ions in the acid side, for example H2SO4, or you have H3PO4 phosphoric acid, right? So here you have 3, right? So this one, if it is a 3 mole of H3PO4, it means that you have 9 normality of H3PO4. Okay, and other acids, right? You have all are these multiple hydrogen acids with multiple hydrogen ions in it. Okay, so for a basic solution, N is the number of hydroxide ions, right, provided by a formula unit of base. So for example, 1 molarity of calcium hydroxide solution is the same as 2 normality of this calcium hydroxide. So note here you have OH, 2 OH, the hydroxide ions in the solution, right? So in the solute. So therefore when we talk about the normality, then we have to take these hydroxide ions in the number of the number of hydroxides into account, right? And if it is NaOH, sodium hydroxide, so it will be the same, right? 2m equals 2n of sodium hydroxide. And then I would also expect you to really have a fundamental knowledge on how to actually making up chemical solutions, or how do you prepare chemical solutions, right? For example, these how many grams of calcium sulfate is needed to make 1 mole of calcium sulfate, right, in 500 milliliter of millicube water, right? This is MQ water is millicube water. It's a very pure, ultra pure water, which means that the water only has this charge, only H2O, okay, only H2O in it. So you it always has these charge and also the water molecule in it, no other things, right? There you have no other contaminants on or pollutants on it in it. Okay, so this is what we call molecule water. Molecule water is useful if we want to prepare, right? When we want to prepare all these solutions, right? We don't want other pollutants to actually or other contaminants to contaminate our solutions, right? We don't want other things other than H2O, right? Other than water itself. So you have a what do you call a machine, right, to actually prepare this type of water. Or previously, right, people use distilled water. Okay, so in the lab, chemistry lab, scientists don't trust this tap water, right? Because tap water inside you have minerals, you have dissolved minerals in it, you have fluoride, you have chloride in it, right? You have dissolved chloride and then you have fluoride in it, you have sodium in it, right? And etc. You have a lot of all these contaminants, we know as contaminants. And when we prepare a chemical solution, right, we want clean, right, water, right? We don't want all these elements to be in the water, right? Say if we want to prepare sodium sulfate, right, in the water, if there is also sulfate, right, then you may prepare if you use tap water, then your sulfate will not be 1 molar, it may be more than that, right? Your sulfate or your calcium will be definitely more than that, because you already have these pollutants in your tap water. So in laboratory work, right, we don't want to use tap water, right? Scientists will use more clean and pure water, for example distilled water, right? And we boil the water and collect what's being condensed, right? The water in its condensed form, and then sort of purify this water, right? So the condensed water will have just H2O in it, right? And then the molecule water also works the same way, right? And it's not boiling, but it's more on the some filtrations, and also the charge of the water. So it is even cleaner, right, than what we have when we distill water, right? So in this case, I would expect you to know how to actually prepare this, right? If I give you a calcium sulfate powder, right, in a lab, and you given some amount of molecule water, and how do you prepare, right? 1 mole of calcium sulfate. So you have to look at the back, or you can check in the internet, right? You can look at the back of the chemical, the label of the chemical. It will label the molecular weight of that chemical, right? For example, the calcium sulfate. So it says that the calcium sulfate actually weight 136.14 gram per mole. So this is gram per mole, right? So this is 1 molar per liter. So if it is, so it means that you need if you want to need 1 molar of these, you want to make 1 molar of calcium sulfate solutions, right? You need to use 136.14 gram. You need to weigh this amount of calcium sulfate and dissolve in 1 liter of water. So dissolve it in 1 liter of water, right? So this is in for one mole, right? But the thing is, here we want it to be prepared, right, in 500 ml of water, right? It's not 1 liter. Okay, so if say 500, we need to keep the ratio, right? So here 1 liter, you have you need 136 gram. You need to weigh this amount of chemicals, right? And then dissolve in 1 liter. But if it is 500, it means that 500 liter, it means that it is just half of it, half of 1 liter, right? So 500 ml, you have half of this, so it means that you have to divide these 136.14 gram by 2, right? Also half, you need half of this amount, right, in this, because we want to keep the molarity the same, the concentration the same. So we need to change the weight of the chemical, right? So by half, right, what we'll get, right? So it's probably around 60 something, right? 68, right? Around 68 gram of this calcium sulfate in 500 ml of water, right? So I expect you already know how to prepare these simple solutions if it is in the lab. Okay, and then this is a making up solution, right? This is the concentration of some chemicals in the solution, and then you have a also you need to know like how to prepare a 10% volume over volume, right? 0.1 normality HCl hydrochloric solution. It's an acid, okay, from a 37% concentration concentrated, right? Sorry, 37% concentrated HCl in a 100 ml volumetric flask, right? So basically this is just volume over volume, so you just take the 10%, right? If it is 100 ml, then the 10% of it is 10 ml, right? So you just need to take a pipette out 10 ml of this HCl, and then you add water to fill up until 100 ml. So it makes 10% volume over volume. So it's just volume over volume. It means that we measure the solution by volume, right? We may use volumetric flask, for example, or what do you call, a beaker, right? Or you have a pipette, as long as we measure it by volume, right? If it is a weight over volume, usually weight will involve dry chemicals, right? For example, those powders types chemical. So if it is weight per volume, it means we need to weigh the chemical, right? Of course, we can also weigh a solution, right? If it is aqueous chemical, aqueous phase chemical, then we can also actually weigh it. So it depends on which one. But weight, right? Weighing a solutions is always much more accurate than looking at the based on measuring by volume, right? Because everything is what they call more accurate when we weigh it under a weighing machine, right? There will be for volume that it is prone to a lot of error, right? You have human error in it, right? It's difficult to know exactly where is the what do you call the mark of the level of it, right? The water level. So there will be some error, right? So weighing solution is always the accurate method, right? So it means that this volume over volume is less accurate, right? Sometimes we want to just want to prepare an acid solutions, right? And a dilute acid solution. So we'll just make an estimation, just so we use volume over volume instead of weight over weight. So if we want to measure and exactly have a calculate or estimate the chemical reaction that's going to happen, right, in when we prepare a solutions, then it is better for us to actually to weigh it, right, to measure the mass or the weight of the substance. So task assigned to measure sulfate and magnesium concentration in alkaline water samples using ion chromatography in the lab. And which is or are the following chemicals in the lab that I could use to generate a calibration curve for the water analysis. So this is a task, right? For example, a task is given to you and to measure the sulfate and magnesium concentration in an estuarine water samples, right? This can be wherever, right? Estuarine, you can be seawater, you can be river water, rainwater. It depends on what you want to look into. And then measure in ion chromatography. So you need to set up a calibration curve, right, to calibrate the machine, right? To calibration actually is useful, right, to check whether if the machine is function well or not, right? If we know, so calibration often involves sample standards, right? So we need to prepare standards, which is a known a solution with a known concentration, say 0.2 molar of in this case calcium sulfate or magnesium sulfate, right? So it means that you have 0.2 molar of this or in the solutions, right? If we can use the just now the method that we prepared these solutions, right? We know the concentration of it, so we may make a standard, right? We know what's inside the solution. There is a 0.2 molar or 200 millimolar, right? So of this sulfate inside. So we prepare like 200 for example, 0.1 molar, 0.2 molar, until you have a 0.5 molar, and then you have a curve, a calibration curve, right? So 0.1 molar, 0.2 molar is here, and then 0.5 molar, and so you build a calibration curve, and then you may check the reading or the concentration of the this is the standard that you prepare, and then here is the reading from the machine to check if it is the reading in your machine actually is consistent with what the standard should have, right? If the instruments give a lower concentration, it means that the instrument is not working well, because if it is 0.05 molar, you measure and get 0.05 molar of sulfate, then it is not like accurate, right? So it has to be compared to a standard to make sure that the machines actually function well, right? So this is just an example of what you should do in the lab. So you are given these analog grade chemicals, right? And with sodium, you have the sodium chloride. This is the molecular weight right behind for the sodium chloride, and then sodium bicarbonate, magnesium chloride, calcium sulfate, magnesium sulfate, sodium sulfide, and a bottle of filtered or certified seawater standard. So please state your choice and provide your reasoning. So what you can use for to prepare these standards, right? So our target is to measure sulfate and magnesium here, right? So we should actually know the concentration of prepare a solution with a known concentration for sulfate and magnesium. So in these choices, what we have here, sodium chloride. So sodium chloride, there is nothing sulfate in, and also there is no magnesium inside, so it is irrelevant, right? And then sodium bicarbonate as well, it is irrelevant because you don't have magnesium or sulfate in it, right? So magnesium chloride here, right? Magnesium chloride, you could use it as you can use it as the chemical to prepare the standards, right? Because it has magnesium, but you can only use it to measure or certify the magnesium, right? You don't have sulfate in it, right? So we can only check the magnesium. And then calcium sulfate, so you have sulfate, right? But you don't have magnesium. The same thing, you can only check the magnesium. And then magnesium sulfate, of course, you have both, right? So this is the best choice, right? When you prepare, then you can actually measure two if you are going to measure both of these ions simultaneously, right? And then you have a sodium sulfide, which is irrelevant, right? And a bottle of filtered or certified seawater standard. So seawater standard, as we know, it may have it has magnesium in it, right? It has a sulfate in it, and a lot more, right? And this certified seawater standard, because it's a standard, so it will give you the it often it will be report, there is a certificate of it, right? You will report the concentration of this magnesium in this seawater standard. So how much? So say in seawater you have usually for magnesium maybe around 40 millimolar, sulfate, right, 28 millimolar, right? So you have these concentration in these seawater standards, and therefore you can use it as your standard as well, as long as you dilute it into the range of your calibration curve, right? A range of your estuarine samples, right? Because estuarines is a mixture of estuarine sample is often you have a freshwater mixing with seawater, so it's your estuarine sample you will often has a less saline or less concentrated sulfate and magnesium, right, in the sample. So you may dilute it with some water, so it will fit into the range of your calibration curve, and then you can therefore compare with your samples and get the correct reading. So estimated concentrations of sulfate and magnesium in the estuarine samples are 18 to 25 millimolar and 40 to 45 millimolar. So what is the choice of the standard calibration range, right? And you are required to make 5 calibration points for each of the elements. So but you only have 5 clean vials in the lab, and state your choice of chemical and calibration range. So these are some of the problems that you have to solve, right? When you are preparing, you are going to prepare a standard solutions for your samples, right? And then also you have to take into considerations the glassware and apparatus available, right? It's not all labs, the labs are not always, you don't get everything what is available, right? Some of it you may have but not have the other, right? So maybe you have 100 ml volumetric flask, but you don't have 200 ml of volumetric flask, so etc. So you have to look at what's available in the lab. So maybe your lab will just have all these, right? So how all these instruments and apparatus and also the glassware, so what you have to decide, right, what sort of things, right, or the apparatus or glassware you are going to use actually to prepare your solutions. So this is the fundamental what is called a thing that we have to do, right, or the decision that we have to make actually to in order to analyze our sample. So chemical equilibria. Next we are going to talk about chemical reactions.